Hello there, Mr. Sutton here, bringing you these AB Calculus 6-3 Extra Practice number 6 solutions on slope fields. On this free response problem, we're being asked to consider the differential equation dy over dx equals this. If I'm being honest, I'd rather not consider that, but we're here now. So our first task is to look at the slope field here, and they're saying a portion of this slope field, a portion of the differential equation slope field is given. We want to sketch the solution curves through 0, 1, which they gave you a little dot for, and also 0, 5 over 2, which they gave you another little dot for. So basic idea, you have to draw a curve that follows the tangent lines and goes through each of these 2 points. But you're going to get 2 separate curves. They want you to graph 2 separate curves, one for each point. So for this first point, we see all these horizontal tangent lines leading in and out of this curve. So it's basically just a horizontal line going through 0, 1. Nothing fancy there. For this other one, though, this is kind of in the middle of these more curved tangent lines. So I'm going to follow the tangent lines going to the left side here, like so. That gives me something that looks like this. And going to the right, let me follow these tangent lines. So we're going like down like this, and then up, and then down again, something that looks roughly like this. So there we go. For this part of the problem, they want an equation for the line tangent to the solution curve in part A at the point 0, 5 over 2. So for a line, a tangent line, we need 3 things: an x value, a y value, and a slope. I'm just going to use point slope to write this tangent line. I don't have to actually use it for anything. I just have to write the equation of the line. But I don't have the slope yet. I have the x value, I have the y value in this point that they gave me. I don't have the slope. So to get that, I'm going to have to plug this point, 0, 5 halves, into my differential equation here. So I'm going to evaluate dy over dx at 0, 5 halves. So I have the y value 5 halves minus 1 times the x value 0 plus 1 times the cosine of, and now I have 0 squared plus 2 times 0 plus pi, all of that stuff. So I guess I could leave it like this because this is technically considered a constant, but I just feel bad not simplifying it. Since it's not the real AP test, I'm going to go ahead and simplify it. So 5 halves minus 1, that's going to be 3 halves. 0 plus 1 is just 1, so multiplying that by 3 halves still leaves us with 3 halves. Next, this is going to be cosine of just pi. Cosine of pi we know is -1, so this comes out to -3 halves. And now putting it all together, using my point slope formula, I have y minus the y value 5 halves equals my slope that I just found of -3 halves times x minus the x value of 0. And this is enough. For this problem, I want to find the particular solution of y equals f of x to this differential equation with initial condition f of 0 equals 5 halves. So this is going to get a little crazy. First thing we need to do is see if we have to separate variables. Since I have a y, an output variable, in the differential equation, that means that yes, I need to separate my variables. So I'll start by dividing both sides by y minus 1. That gives me dy over y minus 1 on the left. And I want to get rid of this dx so that it's not with the y's. So I'll multiply it over to the right side. So I have all the stuff that I didn't just divide by, the x plus 1 and the cosine, all of that with the dx after it. And at this point, it's just about time to take my antiderivatives. The left side here isn't going to be so bad. This is just going to be an ln absolute value of y minus 1, and we'll write that in a second. The right side, though, yeah, this is going to take some work. This is not a one-step antiderivative. In order to do this one thing to pick up on is that I have an inner function, which already, you're probably thinking substitution. And more than that, the derivative of this inner function, which involves an x and some kind of constant, there might be some way to interact that with this x plus 1 out here. So let me try some u substitution. We'll let u equal x squared plus 2x plus pi. And then du is going to be 2x plus 2, all of that times dx. And then if I divide both sides by that, I've got a du over 2x plus 2 equals dx. All right, so we can substitute back in at this point. Now, at some point, I'm going to have to plug in my initial condition, and I'm just going to have to be careful when I do that. because I'm about to express everything on the right side here in terms of u, not x. But I'll adjust for that later on. For now, let's replace this with x plus 1 cosine of u. And then we'll have, instead of dx, I have du over 2x plus 2, which I could actually factor if I wanted to. That's really 2 parentheses x plus 1. So that'll make it a little bit easier to deal with. So now these x plus 1s are going to cancel, leaving me with just 1/2 cosine of u du on the right side. Now I am ready to take the antiderivative finally. Left side then, we have ln absolute value of y minus 1. On the right side, this is going to be 1/2 sine of u plus c. Don't forget about the constant. And to find the c value, this is where it gets a little bit trickier. I need to plug in my initial condition, but as I mentioned earlier, I don't have any place to plug in this x value of 0. I have a y value. I can plug in 5/2 for that. But I can't just plug in the x value 0 for this u right here. Instead, I have to convert 0 into a u value. Fortunately, I know what u equals if I know what x equals based off of this equation I made up here. So if x equals 0, then u is going to be 0 squared plus 2 times 0 plus pi, which basically means u is going to be pi. So right here, plugging in my initial condition really means plugging in pi for the u value right here. So I have 1/2 sine of pi plus c. And let's simplify this a bit. On the left side, this is going to be ln of 3/2. On the right side, sine of pi is just 0, which zeroes out everything there. So we just end up then with c equals ln of 3 over 2. Okay, we can work with this. So I'm going to draw a little line here so that I don't get the stuff down here mixed up with my u work up here. But I'm going to continue right down here now. There's nowhere else to do it. I'm out of space. So I'm going to go ahead and I'm about to plug in ln of 3/2 for c in this equation right here, this general equation, this general solution. However, before I do that, let me resolve this ln of y minus 1 in the absolute value. So to do that, I need to get rid of the absolute value. And to do that, I need to look at my initial condition again, where I see that y in the initial condition is 5/2. Well, if y is 5/2, then y minus 1 is going to come out as a positive number, which means that I don't really need the absolute value at all. I can just replace it with the parentheses, and I don't even have to negate anything. I can just make this ln parentheses y minus 1. Cool. Now, on the right side, I'm still going to leave this as 1/2 sine of u, and then I'll have a plus ln of 3/2. The reason I'm not converting back to x's just yet, even though that's what I really need to do in order to write this as a y equals f of x sort of thing, I'm going to save that until the very end. Let me move things around, and at the very end, I'll replace u with all this stuff that u equals. In the meantime, there's no rush. So to get to the bottom of all this, I need to isolate y by taking e and raising it to both sides. So on the left side, then, that's just going to leave me with y minus 1. On the right side, I've got e to all of this stuff. Now, since these things are being added and they're ending up as exponents that are being added, I could really split that up into e to the 1/2 sine of u times e to the ln of 3/2. E to the ln of 3/2, e and ln cancel, that's just 3/2. So when the dust settles, I can write this right side here as 3/2 e to the 1/2 sine of u. Okay, we can go a little bit further now. At this point, I am going to replace this u with x squared plus 2x plus pi. And just for good measure, I'm going to add this 1 over to the right side so that I have y truly isolated. So there it is in all its beauty, our final solution for this differential equation. For this free response problem, we have the differential equation xy to the 4th. Our first task is to sketch a slope field for that. So I'm going to set up a little table that has all the x and y values in here, and I'm going to lay them out just like this grid is laid out. So I have all the x values from -1 to 1, and then all the y values from 1 down to -1. All right, so let me do each column, one column at a time here. This first column, I'm doing basically -1 times all of these y values to the 4th power. So we have -1 times 1 to the 4th, which is just negative 1. Negative 1 times 0 to the fourth is 0. And negative 1 times negative 1 to the fourth, well, this becomes a positive 1 times a negative gives me a negative 1. Next, we have 0 times all of these y values to the fourth, which is just going to be 0 all the way down because you're multiplying by 0. And finally, I have the x value 1 multiplied by all of these things to the fourth power. So 1 to the fourth is 1, 0 to the fourth is 0, negative 1 to the fourth is positive 1. Let's go ahead and graph these tangent lines. So we have a negative 1 up here. So there's what negative 1 looks like as a slope approximately. And we have a horizontal tangent line wherever we have 0. Here's another negative 1. Horizontal tangent lines all along the y-axis because those were all slopes of 0. And then we have a slope of positive 1 here, 0, and positive 1 again. For this problem, they want us to find the second derivative in terms of x and y, and then determine the concavity for all our solution curves in the second quadrant. So let's go ahead and start with the second derivative. Since I've got x times y to the fourth, I'm going to need the product rule for this. So let me set up my box and ribbon. I've got my two factors, x and y to the fourth, and the derivatives of those, which are 1 and 4y cubed. But hold on a sec. Y itself is an inner function of x. So when I take the derivative of y, I'm really taking the derivative of a something that I have to use the chain rule on. So I have to multiply this by the tail, the derivative of y, which is dy over dx. But hold everything. They want the second derivative in terms of just x and y. So I can't just leave a dy over dx kind of hanging in there. I need to turn it into something that's just x's and y's, such as the stuff that it equals up here, xy to the fourth. So that's what I'll rewrite dy over dx as, just so that I only have x's and y's. All right, now using the ribbon to multiply all this out, I can say my second derivative equals y to the fourth plus, and now we have x times this stuff here. So that's going to be a 4, an x squared, and a y to the seventh, just using some exponent rules. And that'll just about do it for the second derivative portion of the problem. But now they want us to find the concavity of all solution curves given our differential equation, for the given differential equation in quadrant 2. Well, what do we know about quadrant 2? At the very least, we can make some generalizations about the signs of x and y down in quadrant 2. So we're going to end up needing to do a little bit of sign analysis on this second derivative. Now, before I talk more about quadrant 2, just in general, to make my sign analysis of this a little bit easier, I'm going to factor out a y to the fourth. That'll leave me with 1 plus 4x squared y cubed. And that's going to help me basically figure out, is my second derivative positive or negative in certain places. So now in quadrant 2, that is where the x values are negative and the y values are positive. So given that fact, what does that tell us about our two factors, y to the fourth and all of this stuff in the parentheses? Well, y to the fourth, because you have an even power, this is going to come out positive no matter what you do to it. So that's always going to be a positive number. But how about the stuff in here? So if I'm taking negative x values and squaring them, those automatically become positive. If I'm taking positive y values and raising them to really any kind of power, those are still going to come out positive. So this 4x squared y to the third term here is always positive no matter what, at least in quadrant 2. Actually, anywhere really. Well, no, just in quadrant 2 because you have positive y values. But adding 1 to it is not going to change the fact that it's positive. So this whole parentheses then has to come out positive in quadrant 2. So you basically got a positive times a positive, which means the whole second derivative is positive in quadrant 2. If your second derivative is positive, then your original function, which is to say all the solution curves, are going to be concave up in quadrant 2. For this problem, I'm trying to find the particular solution to this differential equation with initial condition f of 4 equals negative 1. I'm going to have to start by separating my variables because I have an output variable, this y to the fourth, in the differential equation. So let me divide both sides by that to get it over with the dy. And instead of writing dy over y to the fourth, I'm going to write y to the negative fourth dy, just so it's easier to take the antiderivative on the next step. Next, let me multiply dx to get it away from the y's. So I'll have x dx on the right side. And now taking my antiderivatives, on the left side I've got reverse power rule going on. This bumps up to a -3 for the exponent. Dividing by that, I have -1/3 y to the -3 power. And over on the right side, this is going to be 1/2 x squared plus c. I have to find the c value for the particular solution. So to do that, let me plug in 4 for x and -1 for y, just my initial condition here. So I have -1/3 times -1 to the -3. A lot of negatives over there. On the right side, this is 1/2 times 4 squared plus c. Well, let's look where the light is brightest here. This is really 16, half of 16 really. That's going to be 8 plus c on the right side. On the left side, this looks like kind of a mess, but we just have a 1 over -1 cubed, which is just 1 over -1, which is just -1. -1 times -1/3 is +1/3. So when the dust settles here, I have +1/3 equals 8 plus c. And to get c, I have to subtract. So this is essentially 1/3 minus 24/3, which is going to be -23/3, which is kind of weird, but hey, it just happened. So now we have to go back and plug that in to my general solution up here for c. So I can write -1/3 y to the -3 equals 1/2 x squared minus 23/3. What a mess. We're still not even there. We still have to get y by itself. So to do that, I'm going to do a whole bunch of algebra and simplifying. One thing I'm going to do right away is I'm going to get rid of this -1/3 by multiplying the whole equation by -3. So that's going to give me just y to the -3 on the left side, which I can just rewrite as 1 over y cubed. Just looks nicer. Over here, this is going to be a -3/2 x squared plus 23. And I'm going to go a little bit further now. At some point, I'm going to have to take the reciprocal of both sides of the equation to get this y cubed out of the denominator. Before I do that, though, I'm going to merge everything on the right side into one big fraction. Just makes it a little nicer to flip everything at once. So we have a common denominator of 2. I can write this as 46 over 2 instead of 23. And then just combining things, I can write 46 minus 3x squared all over 2. At this point now I'm going to take the reciprocal of both sides of my equation. So I've got y cubed on the left and 2 over 46 minus 3x squared on the right side. And finally, to get y truly by itself, I take the cube root of both sides. So we just have y equals cube root of all the stuff on the right there, which gives us our final particular solution for this differential equation.